Good afternoon. Hello, everyone. Welcome to this section, technical session 3, entitled Medical and Biomedical Imaging. The first paper of this section is entitled Border, Boundary and Subregion Denormalization for Semantic Brain Image Synthesis. It will be presented now.
Hello and welcome everyone. My name is Israel and I'm going to present Borde. Brain stroke happening every 40 seconds and every 4 minutes someone dies from this disease around the world. Besides, gliomas are the most common brain neoplasms with various heterogeneous histological subregions. Accurate segmentation of brain images is decisive for diagnostic and treatment. Deep learning have shown promising results in the automatic segmentation, but require a massive amount of annotated datasets. Generative adversarial networks can be used to generate additional annotated training data. Many state-of-the-art models use scene or phase benchmark datasets. We noticed that those datasets differ quite a lot from medical image datasets. In semantic image synthesis, one seminal work is Pix2Pix, which comprises an encoder-decoder generator that takes as input a semantic map and a patch GAN discriminator. In Spade, the authors noticed that the normalization layers wash away the input semantic information. The authors propose using the input semantic map to denormalize or modulate the model activations through a normalization layer. Our proposal is, given the normalized activation map, the denormalization process is given by the calculation of parameters, gamma and beta, considering two important characteristics: spatial variance and instance-specific normalization. Given an a priori input, we propose Borde, a block, to generate realistic-looking brain images. Input information is split over different normalization layers, fed into a set of convolutional and activation layers to learn the denormalization parameters. Our generator relies on the decoder architecture built by Borde blocks. At each stage, the feature maps are first upsampled. Noise is injected into the model in two different ways: a constant Gaussian noise and different auxiliary input in the form of per-channel noise scaled vectors. In addition, residual connections are added to each stage to make the training more stable and to avoid gradient vanishing problems. Our generator be multitask, generating the images of recurrent modalities and also an image of segmentation contours. We compare Borde with two leading semantic image synthesis models, Spade and Sean. We try our proposal and baselines to generate synthetic images and use them as data augmentation in a unit to measure the performance. Additionally, we evaluate FID to measure the distribution between the real images and the generated outputs. Here we have qualitative results. This image shows a qualitative comparison of different semantic image synthesis results with Spade, Shen, and Borde. This image shows different visual results of multimodal brain MRI slices together with their corresponding ground truths. And finally, We conduct two ablation studies on the breast datasets and evaluate different configurations of both the border block and the border generator. In conclusions, we have proposed border and normalization block, and we propose generator. This allows us to probe the need for more domain-specific techniques in GAN's models. Thank you.
Thank you, Israel. Israel, thank you. Your microphone is on now. Okay. Uh, we have here questions from the audience. The one question is from Victor Benitz. So you have tested your model in two data sets, but in the results, we can see that it improves good in cancer data set and little improvement in the other data set. What's the cause of that?
Thank you for the question. This is because the first datasets, the BRATS dataset, have more subregions than the ISLES dataset, where we have only one subregion, the stroke. And in your model, we split this information through different layers, and this makes that take advantage of more semantic information. This is the this is the answer.
Okay, thank you. Also, Senpai is asking, hello, I was wondering, what's the idea of having a constant noise as input?
Yeah. Um, the idea behind the constant input is fit into the generator of the GAN a sketch of the brain, because in your work we are working with brains and the brains have similarities, and this is a technique used in another works, and we find that works well in brain and in medical image data sets and models.
Okay, also, uh, uh, Hugo, some previous works have shown that adversarial training for image translation can hallucinate tumors. Wow, in healthy images. Did you observe these kinds of artifacts in your work?
Okay. We can find some artifacts in the models, but I don't try with adversarial training in our proposal. But exist some artifacts in the models that the models can produce in semantic image synthesis. But we are too working to make or disappear these artifacts now.
Actually, as far as I understood, Israel, you have created the synthetic image just for data augmentation, right?
Yeah.
So you're not producing synthetic image, but those synthetic image that you create for data augmentation, they work as a regularizer, right? For training the network, right? So you probably get improvement in the segmentation because you are using more images uh, in the training set, right?
Yeah.
So you say that the possible artifacts that those images have are not reproducing in the output, right? For new images, right? Or they are not jeopardizing the process. Is that what you say? I mean,
Uh, in the final part of the work, we measure how the data augmentation of your model can be improved the segmentation of brain images. And in this part, now in your work, we don't measure if these artifacts appears in the segmentation, but it's a good question to work.
but I believe they do not appear because otherwise you would have measured errors, right, in the segmentation.
Yeah.
Since you have improved the segmentation mask, it's possible that you did the good job, so a better job, right, in terms of segmentation. Okay, and also, well, I noticed from figure, I think figure, one of the figure two, I got the impression that you're not using the enhanced tumor, but I saw in your table that you use the enhanced tumor. So you're segmenting the necrotic core, the enhanced tumor, and also the whole tumor, or you're segmenting only the edema and the necrotic core.
We are using the same protocol of evaluation in rats dataset that that is core and wall tumor, and I don't remember the name of another, but
Yeah, they have
three
the
parts.
edema that you get from flat too, I think, right? You also use no, four different imaging protocols, right? T1, T2,
Yeah,
T1 with
modalities.
first, and then T2 flare, right?
Yeah, our work produces four modalities besides the contours of the image of the segmentation map.
Okay, and do you know? Are you aware of any work that use only two modalities, the T1 with contrast and T2 flare?
Uh,
Or all works that you saw in this problem, they use the four modalities.
I think it's important use the four modalities because I read the dataset paper, and some separation informations are present in some modalities and not in another. And for
Yeah,
me,
but
I think for
the problem is that in the real life, T1 and T2 are usually, they have only a few slices. So you have to interpolate those images, and they are not volumetric. So you lose a lot of resolution in those images. So that's why I thought, if it was feasible to address this problem with only two modalities, only in T1 with contrast and T2 flare. Right? Okay. Also, I have also observed that you use your technique in the decoder only, right? Not in the
yeah, it's
just.
only our generator is only decoder architecture.
Okay. Okay. Good. Oh, that's fine.
Thank you.
And is it a 2D or 3D segmentation in your
3D,
case?
3D,
3, 2D,
2D, 2D.
2D.
Yeah, so
Okay, good. So thank you, Israel.
thank you,
Congratulations for the very nice work. Okay.
thank you.
Now we are going to, for the second presentation of this afternoon, learning to segment medical images from few short sparse labels. The paper, the work is from Pedro Gama, Hugo Oliveira, Jefferson Santos.
Hi, my name is Pedro. I'm a PhD student at Universidade Federal de Minas Gerais, and I'll be presenting the paper Learning to Segment Medical Images from Few-Shot Sparse Labels. Semantic segmentation is a classical computer vision problem that has many applications in the medical scenario, often being used as a first step in different tasks that can assist in medical procedures such as diagnosis. Although deep learning is the state of the art for semantic segmentation, it is also known that classical deep learning models rely on large amounts of data to obtain successful results. Recently, some techniques such as domain adaptation, self-supervising learning, and meta-learning are focusing on small data problems. For semantic segmentation, we also have the problem that the labels are often laborious to produce, since one has to assign a semantic label to every pixel in an image. Thus, new medical datasets can be costly, since we often require a specialist to provide precise annotations, and the availability of the images are limited due to patient privacy concerns or costly procedures to capture the images. So how can we reduce the cost of new datasets? One option is to reduce the number of labeled images. We call those cases few-shot, and often we have a small number of labeled images, often less than 20. Another option is to use simpler annotations that we call sparse labels. By this, we denote any type of annotation that only a subset of pixels are assigned in a class, in contrast with labeling all pixels. Thus, the primary objective of this paper is to investigate solutions to few-shot semantic segmentation with sparse annotations, and the principal contribution is a novel approach to this problem. First, let's define the problem. We start by defining a segmentation task by a dataset and a target class. The dataset is divided in two disjointed sets called support and query sets, and all the samples are dense annotated. We also define a few-shot task by splitting the dataset in a target class, but in this case the support set is very small and the images are sparsely annotated, and the query set doesn't have any labels. So the problem is, given a set of segmentation tasks and one target few-shot task, we want to segment the few-shot query images using information from the segmentation task and the sparsely labeled few-shot support images. So, our method is called WSLE, a shorthand for Weakly Supervised Segmentation Learning, and it is an adaptation of the MMO algorithm. The core idea of the method is to learn a general model that can be later easily fine-tuned to a target few-shot task. To do so, we present the model several segmentation tasks, where it is first trained with sparse annotations and then evaluated with dense annotations. So we expect that the model learns to minimize the gap of being trained with sparse labels but predict dense segmentations. A detailed explanation of the algorithm can be seen in the paper. The fine-tuning is a simple supervised training with the samples from the support set of the few-shot task. For the experiments, we used 10 medical datasets, but we only evaluated 5 of the chest X-rays datasets. For the segmentation network, we use a smaller version of the UNET network with fewer layers that we call mini-UNET. As for baselines, we used two: the from-scratch baseline, where we train using only the support set of the target task, and the fine-tuning, where we first trained on a selected source task, then fine-tuned on the target task. As mentioned before, we use two types of sparse annotations. The points have a sparse parameter that represents the number of labeled pixels of each class, and the grid annotation has a sparse parameter S that represents the spacing in pixels in the grid pattern. First, we present the results for the JSRT lungs task. In our experiments overall, we observed that increasing the amount of labeled data improves the models, that is, increasing the number of labeled images or shots, or decreasing the sparsity of the labels. As for this task, the WSLE method was the best performing approach overall, achieving high regard score for some of the experiments and even results similar to be trained with dense annotations, for example in some of the grid experiments. The second best performers overall were the fine-tuning baselines, with all three with similar results. It is important to notice that the JSRT dataset is the most distinct between the chest X-rays datasets, which can make fine-tuning difficult. As for the OpenIST lungs task, we observed that the best performers were some of the fine-tuning baselines. In specific, used the Montgomery and Chanson datasets as source, which are two datasets very similar visually to the OpenIST dataset. As for the WSLE method, it was only the second best performer in this task, still with competitive results. Here are some visual results for the JSRT task, and it corroborates with the quantitative results in the sense that increasing the amount of data have a positive effect in the visual quality of the segmentation. And more results are presented in the paper and supplemental material. In conclusion, our method WSLE appears to be the best performing method in the case where the target task is very distinct from the available segmentation task, as was the case of the JSRT tasks, since the JSRT dataset has a different distribution to the other chest X-rays datasets. As for the usability of sparse annotations, our method and even some of the baselines achieved results comparable to their dense counterparts, which implies that using suitable loss functions can work in this case. As for future works, we want to experiment with adapting other meta-learning algorithms for weakly supervised segmentation and conduct experiments with other kinds of data such as remote sensing or volumetric medical images. Thanks for listening.
Thank you, Pedro, for your presentation. Nice work. I'd like to tell the audience that you can send your questions through YouTube or Discord. Pedro, I read your paper and I had a lot of difficulties to understand the paper, the method itself. The paper is well written in terms of English, that's not a problem, but I had a difficulty to understand how the method works. And the video did not help much because it was too fast, right?
Okay.
So let me ask you something. So you have you present in the paper different types of annotations. So I saw that you have the dots, right?
Yeah.
You have like a grid sampling with annotations, right?
Yeah.
So you have different types of sparse annotations, and you train the model to predict dense annotations.
Yes, right.
Yes, but you do the training only on those 10, 20
Labeled pixels.
No,
And images.
image,
Yeah.
right? Okay, so you have only, let's say, for a 20 shot learning, you have 20 training images,
Yeah.
and those 20 training images are also weakly supervised in the sense that you have only one of those markers, right, in the image.
Yes.
Is that the case? Okay, and then you train the method to predict the dense annotation of those 20 images.
No, the remaining images. So
Okay,
we defined that task, but right. So we have a data set divided in two sets: the
okay,
support set and the query set. The
okay,
support set is used for training, so we sample 20 images and only sparse annotated with 20 pixels, for example.
okay.
And then we compute the loss using the query images later, and which is the reminder images in the data set.
And then this data set, the support data set has, no, not the support, the query data set has, uh, it has to have too many images or with dense annotations or,
For the support tasks in the meta training, yes, but the few shot task, that is our target task, no. So in the first step, the meta training, the dataset already has dense annotations, but for training, we specifically force the methods to train with sparse annotations. So we generate sparse annotations from the dense original annotations.
okay, okay. So let me see. You have actually a kind of training set that you call the support set, right? With
Okay.
sparse annotation. You have a kind of a validation set that's called the query set with dense annotations and
Yes.
lots of images with dense annotations, right?
Yeah.
And then you learn the model with these two sets. And then when
Right.
you go for the test set, then you have another type of query set which has only which could have only one image, for example, but the test set with no dense annotations, and you want to predict those dense annotations. And of course, you have the dense annotation just to measure the performance, right?
Yes, exactly.
Okay, so why is this called a few shot learning in the sense that since you need a lot of images with dense annotations to learn the model?
The idea of the few shot is for the target task. So the target task have only few images, and these images are sparse annotation.
I
But before this, the training for this target task, we use the supporting tasks, which are these datasets with dense annotated images.
And also, if you have these images with sparse annotation, first, what kind of sparse annotation you are using?
In
The
this case, we are using the points and grid annotations, which are the
Okay,
two that we are evaluating.
and then for that point, so all you try to you try to predict the dense annotation from those points. So do you have any kind of label propagation from those points in order to?
No, in the as I said, in the target task, the support set have this annotation image, but the images used to compute the metrics or the query images doesn't have labels, so we can't propagate these labels. We could for training, but we don't. We only use uh, the sparse pixels that are labeled. So for training, we only use, for example, 20 pixels to compute the loss in a supervised manner.
Okay, so the loss is only computed based on those markers.
Yes.
So you're not using the dense mask of the query set to compute the loss.
No. For the target task, no.
No, I mean during the training.
During the training, yes. So the training is divided in two parts: the meta training, where we have these tasks with dense annotations, and the fine tuning, where we train for the target task.
I see. Okay, interesting. So um, I thought that. Do you think because I mean the model needs to know somehow how to propagate labels to all pixels, right? Even
Yeah,
if the learn is only from a few markers. So I was wondering if you could use any other or even image processing tool, for example, that works from markers to create pseudo labels and use those pseudo labels to increase the number of annotations and by doing that improve the model, for
yeah.
example.
In fact, we are investigating some some of these techniques to expand
Wow.
some of the markers.
Okay. Okay. So I'm not going to give the spoiler of your next paper. Okay, so the audience, if you do not have any extra questions, we can move to the next presentation. Thank you, Pedro, for your presentation in Word.
Thank you for your questions.
Okay. Okay, the next paper is a new grammar for creating convolutional neural networks applied to medical image classification. It's the authors are Kleber Silva, Pericles Miranda, and Felipe Cordeiro.
Hi everyone, my name is Kleber Silva and in this video I'll be presenting our work called A New Grammar for Creating Convolutional Neural Networks Applied to Medical Image Classification. In recent years, the adoption of convolutional neural networks, or CNNs, has been highlighted in solving computer vision problems such as image classification. Several networks architectures were proposed with different sizes and complexities, and an increasing size of trainable parameters. Thus, finding an optimal CNN architecture configuration with reduced complexity and high performance became a difficult task. Seeking to solve this problem, researchers added the automation of CNN configurations in optimization problems. Several techniques have been proposed, including neural evolution and the use of genetic algorithms. However, the results obtained in some works show that grammatical evolution is a promising technique for optimizing CNNs. Using the principles of grammatical evolution, this work proposes the use of a multi-object revolutionary algorithm, or MOEA, associated with a new context-free grammar responsible to generate and map the CNNs. The MOEA optimizes the networks by maximizing two objective functions, the accuracy and F1 score. The optimization was done on a newly published medical imaging dataset collection, the MedMNIST. In this collection, we choose three multi-class datasets that present more images, the PathMNIST, OCT-MNIST, and OrganMNIST XL. This is our proposed grammar in BNF's notations. It is capable of generating 6,426 different network architecture configurations. Its structure can range from classic CNN layers, such as convolutional, pooling, and fully connected layers, as well as network optimization layers, such as Bayes normalization and dropout. In addition, the grammar has parameters that can be changed to increase or decrease the amount of the individuals generated, thus altering the optimization space. Other CNN's parameters remain fixed to simplify the grammar. To evaluate the proposal, we divided the experiments into three phases. In phase 1, the MOEA is run for each dataset with a population of 50 individuals for 30 generations. Each individual represents a CNN that is trained 3 times over 70 epochs. The averages of the accuracy and F1 score of the networks are computed. In phase 2, an individual from the Pareto front of the MOEA is selected and trained 10 more times, along with another 4 state-of-the-art networks and another 2 networks generated by other grammars. The network's accuracy and F1 score averages are computed again. Finally, on phase 3, the results of the networks are compared. After the experiments, the results showed that our proposal achieved the best performance in the PathMNIST dataset. and competitive results associated with a minimalist design compared to the other networks in the other two datasets. It is important to emphasize that our networks have an average of 89.18% less trainable parameters compared to the DenseNet 169, which ranks first in the other two datasets. Furthermore, they are smaller in size, have fewer layers, and a shorter training time. We performed a test of the statistical significance of the results in initial method, where the null hypothesis is that there is no statistical difference between the means of the network's matrices. The null hypothesis was rejected, showing that at least one result is statistically different for the others. To identify statistically equal groups, we apply post hoc naming and calculate the critical difference plot of the data. The graphs show that our proposal generated networks with the results statistically equal to the first places in all datasets, showing that our proposal is an interesting alternative in creating low complexity and high performance CNNs for classification problems. The results show that our generated models reach a prominent position both in accuracy and affluent score in all datasets, being equivalent to networks like DenseNet 169 when compared statistically. However, our networks used less parameters compared to the DenseNet 169, showing that our models are effective and efficient, with a simpler architecture and consuming less computational power and training time. As future work, we plan to update the grammar, adding other regularization settings. We also intend to add other important metrics that help in the convergence of the MOEA. That's all. Thank you.
Okay. Hi, Clever.
Hi.
Congratulations
Thank you.
for the work. I I like very much the fact that you use the statistical test, something that's very rare.
Oh, thank you.
Okay. Uh, the audience did not send any questions so far, so you guys can send questions through YouTube or Discord. Please do so. Kleber, I saw that in this work, it was not clear to me. For example, you compare with baselines, but were the baselines pre-trained on ImageNet?
Oh, no. We didn't use the transfer learning for ImageNet. We only used the CNNs with the default parameters.
But no, not for your work, for the baselines, that the works that you compare with the methods,
Yes.
the other ones. So you use the DenseNet pre-trained on ImageNet, right?
Right.
And you compare with your network, uh, the architecture selected by the algorithm, trained from scratch. Was that the
No,
case?
we compared the DenseNet V169 and the other state-of-the-art networks in the same dataset that we trained our networks generated by the grammar.
Okay, but the initial weights.
There is no initial weight, only the default parameters from the state-of-the-art networks.
Okay. So no, I was just wondering if when you use these state-of-the-art networks, before you do the fine-tuning in your data set, if these networks have been initialized with the weights learned from the ImageNet. I believe so, right? So you just
I see.
okay. But anyway, I think the fact that your approach was able to find a simpler architecture with similar results, right, is very nice. Okay.
Okay, thank you.
My question is actually I did not understand why some of the hyperparameters that I believe are important for training have not been included in the process of finding the architecture. For example, the batch size. Do you have an explanation for that?
Okay, when we created our grammar, we focused to create a grammar with a reduced search space because we saw that other related works had such space almost infinite, with infinite candidates solutions. So we created a grammar with a search space with only I think that are 4,000 individuals for creation.
I see.
So
So you have a limit in the number of the number of individuals in the population.
yes, to help the confidence of the MOEA and reduce the training the time of the generations of the MOEA.
Okay. Okay. Oh, that's good. That's good. I think I didn't. I like very much the paper. I didn't have. It was pretty clear. I had like a couple of questions on. One is
Okay,
this question that I made, and the other one is the that I that I asked you, and the other one is the why you did not use another metric like kappa, for example, because some of the metrics that you use for the work they are sensitive to imbalanced data sets, right? So they might uh, produce, let's say, a very high accuracy, but because they are choosing the bigger class always, right? Uh,
okay,
so I believe that if you use the kappa, for example, this could actually play in favor of your method also. So in the case of
okay,
those deep neural networks, try to have very high, let's say, very high F score, but when you use kappa, then it will reveal if some of these classes are not being predicted correctly, right?
okay. That's a good improvement. We are planning to add other metrics to the other our next paper that will be published, and we think to add four metrics in general for uh, fitness function to optimize the CNNs. And the accuracy, the F1 score, and the other two, we can, for example, add the kappa
Mhm.
to increase the confidence of the model.
Okay. Okay, Clever. Thank you very much. Let's move to the next talk because of the time. Okay, then the next talk is the paper is entitled Improving Similarity Metric of Multimodal MR Brain Image Registration via a Deep Ensemble. Nathan Andrade, Fabio Faria, and Fabio Capabianco are the authors.
Hi, my name is Fabio Capabianco, and on behalf of the authors of this paper, Nathan Andrade and Fabio Faria, I will present this work entitled Improving Similarity Metric of Multimodal MR Brain Image Registration via a Deep Ensemble. Our work consists of medical image registration. Image registration is a problem where a geometrical transformation moves a source image onto the same space of a target image in order to have their contents overlapping. Our work focused on the similarity metric element of the registration applied to multimodal images. Multimodal images are images that have the same content with different appearance, such as this example here, where we have T1 and T2 images of the brain that are acquired with MRI scanner. This slide shows our main methodological contribution. We proposed a deep ensemble to compute similarity maps. Starting here from the left, we have, during the training, pairs of patches that are inputs to the network. They may be both from corresponding or non-corresponding regions. Then we use any number of metrics, both classic and deep learning based, to compute several different similarity metrics, resulting in those maps. After that, we may select any subset of those maps and use them as input to our deep ensemble. The ensemble here is also a CNN and an autoencoder. The ensemble has been trained to learn from the maps as their inputs, and our final result as output is also a similarity map. This approach was designed to be feasible both in terms of required space and computational effort. The second contribution of our paper is proposing a novel evaluation metric. Traditional metrics did not reflect the desirable features of our similarity metric. As the output patch is small with respect to the image, traditional metrics failed to elucidate simple information, such as, did the method point the highest probability at the point of interest? How many false negative regions are there? The idea is to generate two simple measurements. The first one, PPOR, is a binary measurement that indicates if the transformed patches match the target patch and has a similar size to it. That's because some methods assign a high probability to a large area of the image containing the target, but this is not useful. The second measurement is FPOR and is a quantitative measurement that provides the approximate quantity of false positive patches. Again, large patches may count as multiple false positives in this metric, depending on their relative size to the patch size. So here we show some qualitative results, and our method here, ESB3 and ESB5, got the best results. And here we show our quantitative results. And as you can see, according to both classical metrics, our ensemble got the best results. Also in terms of false positive in our new evaluation metric. CNN21 got a very good result too, and even better than ours in terms of true positives, but it got 7 times more false positive results. And finally, we want to thank CAPS for financial support for Nathan Andrade Master Scholarship, and also NVIDIA for donating a Titan V GPU for our research lab.
Hey, Fabio. Nice. Congratulations for the work. If you don't have questions to YouTube or Discord, so I ask the audience to make them, please. Fabio, in this work that I understand that you are trying to combine metrics, right? For instead of using only mutual information, for example, for registration, is the idea to combine metrics, but in what stage of the registration? In the stage of the deformable registration? I mean, when you already did some kind of rigid registration, then you want to do the deformable registration locally there, and then you're going to do that based on patches and multiple metrics? Is that the idea?
Well, actually, before that, thank you for being here at SIBGRAPI, and thank you for being with Professor Alexandre, was my advisor during my PhD. And answering the question now, the registration process, it has both in the first stage, that is a registration, and also after that, in a deformable registration, it requires that you use a similarity metric to compare and to measure how good the registration process was.
Yes.
And
yes.
you can use this metric in both stages.
Okay.
In the sense that we are trying to improve the current methods, the current similarity metric methods, to have a better matching of the regions.
So, but then, for example, I understood that you extract several metrics and then combine them. Is that the idea, or you did that just to select to show that the one based on the network is better? Now you combine.
Actually, yes, we use a deep ensemble, which may use both classical metrics and also deep metrics as inputs. You use many of them, and then you combine the results by an ensemble, which is more intelligent in the sense that it is capable of getting the best of each of those methods and outputting a better metric.
Okay, but this doesn't make the registration slower. I mean, less efficient in terms of, because it becomes more complex, right? The final metric is more complex, right?
Yes, it's one more step that you have to add to your registration process, because the all the similarity metrics that we use, they may be they may run at the same time. And but after that, you have another step that is the deep ensemble, which is the time for executing a relatively small deep network. It has just nine layers.
What's the impact in terms of computational time in the registration when you use this approach?
Well, actually, we didn't do the entire registration procedure here in this paper. We just proposed the methodology to compute the similarity metric. But we believe that it may double the time of the similarity evaluation. Yeah, not the full registration, because the registration also includes the formation process, which is a transformation, and also the optimization step, which compares the results of many attempts in order to make the registration.
I see. That's interesting. But so you did not try it yet on any deformable registration, for example, because you could include that in elastics, for example.
Yeah, sure. Actually, I'm talking to another author here that came with an interesting point, that if you have a better evaluation, you may even achieve the registration faster, because you may the optimization procedure may be
They
optimized.
converge faster. I see.
Yeah, they converge. Yes, that's the point.
That's true. That's true. It's interesting. And then you also have so far made experiments in using 2D patches, or you
Yes.
did not try 3D yet, right?
No, we just used 2D patches, and as we used the small patches, we focused more at the step of the deformable registration, because the initial registration is the use the
global
image. Yes.
Oh, that's good. That's good. Thank you. Interesting.
Thank you.
Okay, Fabio. Let's move to the next speaker then. Okay, the talk now is entitled An Approach Based on Image Processing Techniques to Segment Lung Region in Chest X-ray Images. The paper has authors Luisa Menezes, Augusto Araújo, and Aura Conci.
Hello everybody, my name is Luisa and I'm here to present an approach I have been working on with Augusto and Aura regarding an image processing technique to segment lung region in chest x-ray images. So our goal is to go from a chest x-ray image like this here and produce a segmented lung image, a binarized mask. And the reason why that's important, well, first of all, radiographic images are an indispensable tool regarding clinical investigation for physicians worldwide due to their speed, convenience, and simplicity. Well, as Cal and Zell point out, one of the most critical radiographic analysis tasks is lung segmentation. And why lung segmentation is important? Well, many authors have shown that applying a lung segmented image to a neural network for a classification problem actually improves the results. So we hope that our method can help to produce better results in classification problems for diseases such as COVID-19 and tuberculosis, for example. We also want our method to be more accessible. As we are going to show during the presentation, many of the methods used for lung segmentation uses some kind of a neural network, and that's very costly. You need there is a dependence of a high number of images to train. Their complexity is high, and we want to use only image processing techniques that enhances the performance, and well, it helps to reduce the environmental impacts of machine learning algorithms in general. In our presentation, we are going to show step by step how our method works, but I can tell you beforehand that our approach is based on identifying non-regions first so that we can actually find our region of interest through a binarized image that can serve as a mask to any other more complex algorithm. We are also going to show the results of our work both in terms of a qualitative approach and in terms of a quantitative approach in numbers, comparing with other studies, and also presenting some conclusion and future improvements regarding our work. Thanks for watching and see you there.
Hello. Hey, Luisa. Hi, how are you?
Hey, I'm good, and you?
Fine. Let me see here. We do not have any questions from the audience yet. So let me understand. Your approach is only based on mathematical morphology operators, right? And you got interesting results in the data sets that you tested. But those results, as far as I understood, they are not better than the results that you get with the deep neural networks, right?
Perfect. Yes. The performance actually gets better in terms of time. So our amount of time to calculate those masks is very short. So it's 0.0006 milliseconds, whereas when you use like neural network, yeah, then it's higher.
Yeah, I saw that, but what I was imagining here is that, okay, if you want to analyze the content of the lungs, right? All you have is to have a mask that it might not need to be a perfect delineation of the lung, as long as it's good enough to include the anomaly, let's say, inside the lung, right?
Yeah, so, I think that's the idea, because when you apply the mask, then you are going to use another algorithm after to proceed and do some classification problem, some kind of thing like that. And yeah, you don't actually need to have it perfectly designed. So it's a good approach because you have this time advantage.
Okay, and you can process a huge amount of image. For example, for the X-ray case, you usually have a lot of image, right?
Yeah, on this case, we only tested with 24 images. So that's also some kind of advantage on using this kind of approach, because on the medical field, it's very hard to get all those labeled images as the work. I forgot the name of the other guy. I think Pedro. He presented. Yeah, he presented a similar work, and yeah, they needed to use a lot of images. And on this approach, we only used 24. It would be good if we could do more on that, like tests on other samples to check the accuracy and the other indexes that we
Yeah, but
evaluate.
did you use 24 to adjust the parameters of the method, or you as no,
No,
you only use 24 for the whole work?
yeah, we don't have like a testing step, so we don't need to put a huge amount of images on the method to work.
Okay.
It is an algorithm, like you are
Yeah,
just going to pass the image and it's going to get out.
okay, but the validation of the method use only 24 image? No, the
Yeah,
validation of the method use
yeah, we only use it 24. Like on
so
the other work,
how do you know how this will perform if you had, let's say, 2,000 images?
you will need to pass it through the algorithm for the 2000 images.
Yeah, because
But then you would need a ground truth, right? And that's the big problem when it turns to medicine field, because you need the ground truth. You need how can I say? You need a
I
doctor
believe yes,
to
yes.
evaluate and check if that's correct. So you need a specialist.
I
And
think it's a good idea if you talk to Pedro, because I believe he has the ground truth for the data sets that he have. He has worked with these data sets. I mean, Hugo and Pedro both are co-authors in that paper. They have worked with X-ray images for lung segmentation X-ray images for some time now. So I believe they already have examples of X-ray CTs, X-ray data with segmentation. So maybe you can talk to them to get this type of data set. I think there are two things that you can think about. One is maybe this is a good idea to evaluate if you are able, for example, to segment to include the anomaly. For any data set where you have anomalies annotated, if the anomaly is inside or outside the mask, this could be more important for you than measuring the accuracy of segmentation, because you are not actually interested in the accuracy of segmentation. You are interested in if you are including or not the anomaly inside the mask. Okay. And the second thing is you could also try to use the labels that you produce with your method to train the network, because although they are pseudo labels, there are some errors. They could improve, they could provide a kind of data augmentation uh, with pseudo labels, of course, right, to train the network. And this could produce a better network that could be used for the case where time is not a problem, right?
right. Yeah, we had a specialist on our team, a doctor. So Augusto is a doctor, and he did the masks. He took about 40 minutes to do each of them. And we also provided them through the GitHub website. It's in our paper. So if other people want to have access to the database that we used, even the code, everything's there to share.
Okay, thank you. Okay, thank you, Luisa.
Thank you. Thank you for your considerations.
Okay, bye-bye. So now the paper is automatic segmentation of posterior fossa structures in pediatric brain MRIs. Hugo Oliveira, Larissa Penteado, José Maciel, Sueli Ferraccioli, Marcelo Takahashi, Isabel Bloch, and Roberto Cesar Jr. are the authors.
Hello, my name is Hugo Oliveira. I'm a postdoctoral researcher at the University of São Paulo. I'm going to present to you the paper entitled Automatic Segmentation of Posterior Fossa Structures in Pediatric Brain MRIs. Magnetic resonance is a useful tool for assessing the healthy development of infant brains, allowing for the detection of multiple abnormalities, such as tumors, congenital malformations, and hypoplasia. Thus, the segmentation of some areas of interest, such as the posterior fossa structures, is very valuable in clinical settings. However, no public datasets of brain MRIs covering the whole spectrum of infancy, that is, between 0 and 18 years, is available in the literature. There are also no datasets with labeled organs in the posterior fossa region with this age cohort. Therefore, our team decided to create our own dataset in collaboration with radiologists from Instituto da Criança, University of São Paulo. In order to scale the study of posterior fossa structures, we employed machine learning models to conduct the segmentations according to the annotations provided by the physicians. Before presenting our segmentation strategy, we will provide information about our dataset. The 32 volumes acquired by our team are T2 sequences with 4 labeled structures: the fourth ventricle, the brainstem, and the cerebellum. Preprocessing consisted of skull stripping and bias field correction. As you can see in the rightmost part of the slide, most samples are concentrated in lower ages, that is, between 0 and 4 years. 3 samples in our dataset and crops from regions of interest in the posterior fossa structures can be seen here, together with the annotations provided from the specialists. Aiming to improve the segmentation performance, we opted to use an ensemble of segmentation architectures, instead of focusing on one single design philosophy. These networks are the 3D-UNet, the VNet, the HiResNet, the SkipNet 3D, and the Med3D network. You can check out all the details of these architectures in our manuscript and in the publicly available source code provided for this research. In our proposed framework, each architecture is first fed a downsampled version of the MRI volume in order to produce an initial coarse segmentation prediction. However, early experiments showed that these initial segmentations were very coarse and tended to produce inconsistent boundaries between classes, even with the use of patching strategies. With this in mind, and in order to account for the large label imbalance in underrepresented classes, we proposed a pipeline with specialist networks. Initially, the generalist network provides a coarse segmentation prediction. This is used to extract 3D crops containing the organs of interest and some padding with surrounding tissue. The first ROI, X1, focuses on the brainstem, in yellow, and the fourth ventricle, in green. The smaller volume is used to train the specialist network, S1. The second ROI, X2, feeds the second specialist network, S2, on segmenting the cerebellum. In the end, a fusion function phi uses the output of the generalist and both specialist networks to provide one single fine-grained prediction. This pipeline is trained for each one of the 5 network architectures individually, and their predictions are merged using majority voting. In order to properly evaluate the performance of the generalist and specialist settings, as well as the majority voting, 3 distinct quantitative evaluation metrics were employed. These are the voxelized dye score, 2 variations of surface distance metrics, and the R2 correlations between predicted and manually annotated volumetries. These 2 tables summarize the results of voxelized dyes and the surface distance metrics for a specialist pipeline and a generalist pipeline as a baseline. We also include individual segmentation architectures for the dice metric, in comparison with the majority voting. As you may see in the highlighted results, both the majority voting and the use of specialist networks consistently improve the performance of the algorithm on dice and surface distances. The correlations between manual annotations on the y-axis and the network predictions on the x-axis also improved by a large margin when employing the specialists. The best R2 for the brainstem reached 0.83, while the cerebellum volumetry from the specialist network and the radiologists were highly correlated, reaching 0.94. At last, we present some qualitative results for the same volumes shown previously on this presentation. Relying simply on the generalist networks yields very pixelated boundaries between classes. When using only the S1 specialist, the segmentation of the brainstem and the fourth ventricle is clearly improved, but there are inconsistencies in the boundary with the cerebellum. All of the aforementioned problems are considerably mitigated when using both specialist networks, wherein the boundaries are clearly delineated and very close to the ground truth annotations. As our final remarks, we observed that the agreement between ground truths and predictions was high even in a very small data scenario with only 32 samples. Also, the use of specialist networks and majority voting proved to be a highly successful strategy for the segmentation of posterior fossa structures. At last, given the accuracy of the volumetry predictions, our pipeline could be used to define volumetry standards for healthy pediatric neurological development. Future works include the analysis of developmental abnormalities in our dataset, gathering additional unlabeled data from Instituto da Criança for the creation of the volumetry standards, and testing our pipeline on the recently published FETA challenge. Our team is composed of graduate students, postdoctoral researchers, professors, and radiologists. On the rightmost side of the screen, you can access the GitHub for this project via the QR code or the link. The authors would like to acknowledge the financial support provided by Fundação de Apoio à Pesquisa do Estado de São Paulo and Agência Nacional da Recherche.
Hey Hugo, how are you?
Hello, Falcão. You okay?
Yes. Nice work. I remember that I heard from Roberto that he was getting involved into this project. It's nice to see that the project is advancing. I have a question for you, but before that, I'd like to again tell the audience to send messages through YouTube or Discord, because I cannot see any questions here. I see that you, the traditional pipeline for, let's say, for segmentation, using networks, is that you, for example, you could use a kind of object detection, right? Network followed by segmentation of the detected region, right? So my first question is that when you decided to replace object detection by a segmentation network, like a UNet network, right? That provides a coarse segmentation, which is your GNet, right?
Yeah.
Did you compare these two possibilities before you take this decision, or you just went straight forward to the second option?
Yeah, the first idea was to use patches actually, because we kind of thought that that would be good enough for the segmentation of the fine-grained boundaries between regions. But this turned out to be not optimal, as we showed in the presentation.
Okay.
What happened is we only had 32 labeled samples, and data augmentation showed to be very
Not enough.
unproductive for this first segmentation, for the core segmentation. So we decided to use a more dense segmentation instead, architectures as a UNet, a VNet, a high-res-net, etc., instead of a boundary box prediction network, a 3D detection network as a fast RCNN. That was basically the motive, the number of samples and the density of the sampling.
So, but do you believe that if you had more samples, more annotated image would be valid, for example, to evaluate detection network on sub images on Windows, like you slide Windows and instruct and apply a detection network to verify if you have the object of interest inside or not, and then for those that are positively detected, then you apply the specialist network to do the segmentation. Do you think this would be interesting to try later, or are you satisfied with the approach that you took now?
Yeah, we have already, I think, more than 70 other samples that are not currently labeled, and we are working with a radiologist from Hospital das Clínicas, from USP, to label these images based on the first predictions of this first method that was trained on these only 32 volumes for the initial data set that we used. So we might transition to a more, let's say, robust boundary box detection method that's a fast RCNN, PSPNet, and etc.
Yeah, and for your particular case, I don't think that, for example, the size of the regions is the issue, right? Or is this
some of them
could be a problem? It could be a problem because if this coarse network, I understand that it's being applied to the entire image. Is that the case? The entire brain image?
Yeah, a downsampled actually version of this image, and there is a major problem with labeling balance actually, because we have a cerebellum, which is a relatively large organ in the brain, in the posterior fossa structure, and we have also the fourth ventricle, which is very small. So we had also we didn't know if a fast RCNN, for instance, would correctly detect the small structure in the posterior fossa.
Yeah, that's why what I believe that if you use I believe that you really need two specialist networks, one for the small, one for the big, because of the strides will be different in each one, right?
Yeah.
The strides that you're going to use for the networks. But for the G network, the one that locates the object. I think it's a nice idea to use that. Actually, I like that idea better than than the idea of using Windows. However, I believe that idea also could bring some false positives. So I'm wondering here that what you have done to eliminate the false positives of that course segmentation and focus on the true positives that actually were used to guide the extraction of the smaller window for the specialist networks.
Yeah, we already began some tests on the unlabeled images, the 70 plus unlabeled images that we have, and we detected some false positives on this first course segmentation. So this might be a problem when we escalate this to much more data, much more larger data sets. There is a very novel data set, which is called the FATA data set, FATA, for fetal brain images that has a lot of annotations, including the organs that we studied in this project. We did not use this data set, first because it is from fetal images, so it's only from neonatal patients. We don't have this age cohort between 0 and 18 years. And secondly, because it was recently published on MICAI 2021, so we didn't have access to that on last year when we proposed this method.
I see. Oh, I'm curious to see how this will proceed. Also, the pre-processing of the images is something that you might want to get in contact to one of my former students, Samuel. Actually, we have in our lab a pipeline for pre-processing MR images and create the brain, just the brain, right?
Yeah.
But with also bias correction, all this kind of inhomogeneity correction procedure, right? Because what I have observed, for example, depending on how, if you are using BAT for skull stripping, so if you are using the traditional approach that you can find in ITK, those softwares, depending on the way, the region where the image was acquired, if you get, let's say, more neck than other images, these methods can lose part of the brain, can miss part of the brain. Right?
The BT is quite inconsistent in some samples of ours, but none of them cut an important part of the brain for this work, at least, that we observed. So it might not scale that much better to the larger data sets or more diverse data sets.
Yeah, I believe that we have this standalone code that I think you can use to do the pre-processing and extract, for example, the brain already pre-processed and standardized, and then from that point on, you do the work that you are doing. So I think this could help you on this step.
That's great. I will contact Samuel, certainly.
Yeah, or you can send me a message. I put you in contact to other students in the lab, and of course, copy Samuel also, so they can help. Okay?
Okay, thank you very much.
Okay, Hugo. So let's move then to the next talk, I think, right? The gated recurrent conditional generative adversarial network, GRC GAN, application to denoising of low-dose CT images. The paper is authored by Matheus Baltazar de Almeida, Luiz Pereira, Sang-Bin Ren, George Cavalcanti, and Jan Sybers.
Hello everyone, my name is Matheus Baltazar. I'm here to quickly present our work entitled The Gated Recurrent Conditional Generative Adversarial Network, GRCGAN, application to the noise of low-dose CT images. The computed tomography technique is very used to make medical diagnostics, which needs to visualize internal body structures. However, this process uses the ionizing X-ray radiation, which damages the patient's health, especially the ones who need to do this frequently. To reduce the damage in the health of patients, the quantity of radiation can be reduced if there are methods to recover the images that will be with noise because of the reduction of the radiation levels. Our problem came from there. From a low dose of radiation capture, we need to generate a new image which represents the versions of the image captured with the normal dose of radiation, which has much less noise. We also want to solve this by getting a better result than the generative adversarial network applied in the same problem. Observing the good efficiency of the recurrent neural networks applied to problems as natural language processing, audio processing, and video processing, our main motivation here is to apply these recurrence to the CT image denoising problem. Regarding LDCT image recovery, when we applied a recurrent method to solve this problem, we would be the first ones to use this approach. In other words, we would be inaugurating this application. To build our method, we made an adaptation in the convolutional gated recurrent unit, and we use this structure as the generator network of the generative adversarial network, forming our gated recurrent conditional generative adversarial network, GRCGAN, as shown in this illustration. In this case, the recurrence will be applied t times, and after each recurrence will be produced by the generative network a version with less and less noise. About the results, the top image represents 4 versions of a sample. Its trivial version, LDCT, the results of SIGAN and GRCGAN executions, and its version without noise, the ground truth. The bottom image represents the difference map between the results of the execution of 2 networks and the ground truth, where the dark pixels represents a greater distance. The results are promising and demonstrate well the effectiveness that the proposed architecture has in relation to SIGAN. Using this table, we can compare the mean values of standard deviation of matrix executions, utilizing the same database for both networks. The proposed architecture got a better average value on all metrics, highlighting MR, MSE, and PS and R. Concluding, we constructed a gated recurrent conditional generative adversarial network, and by analyzing its operation, we identified that the gates helped the network by guiding the execution at each recurrence. Comparing the performance between the proposed method and SIGAN, we observed that the proposed method has a performance 36% and 17% better than SIGAN in relation to NR, MSE, and PSNR metrics, respectively. Thank you for your attention.
Okay, thank you, Mateus. Nice.
Thank you.
Yeah.
Thank you.
Do you, when you, I did not understand very well, how did you measure, how did you validate the approach actually? You have a CT image as
Yes.
the real image, as the ground truth. Is that correct?
Yes, it's correct.
And then the low dose image is a simulated image that you simulate the low dose from the CT, or it's a real low dose image from the
No,
same.
it's not a real low dose. It's a simulation.
It's a simulation. I see.
Yes.
And that simulation is very realistic, I believe, in terms of creating artifacts.
Yes. The noise is is put in the image using the Poisson noise.
Okay. It's a Poisson distribution. Poisson.
Yes.
Okay. The other thing is that okay, because it's a simulated. For instance, have you used or have you thought to use, for example, this approach for metal to remove metal artifacts? Because I guess that in the case of low dose images, metal artifacts can be a trouble, right? Because
Yes.
you're going to get a lot of noise, right? A lot of artifacts in the image from the metal.
Mm-hmm.
Do you have this in your data set? I mean, or you did not try it yet?
We didn't. And about the noise, it's very delicate because it's people, and I'm very anxious. I'm sorry.
No. Oh, good.
People's. It's not cool to get a lot of radiation. Yes, and it's the mean about the simulation of the noise.
I see. Yeah, because I mean, there are some, for example, perhaps you can consider, for example, to do some work with people who has who have, for example, a low dose CT, like an OCT in dentistry, or I mean, some areas people use this, right? The low
Yes.
dose CT, and if you use the low dose CT and apply your approach, for example, as a test set, and then you can try, for example, to of course, you're not going to have the ground truth of the real CT because the whole purpose was to to avoid the radiation, right?
Yes. Yes.
But then you can try to figure out some kind of indirect evaluation or subjective evaluation for the work, for example. For example, if the idea is to remove artifacts that can be facilitate segmentation, then you could, for example, do interactive segmentation for the validation, and then and show that the segmentation, whatever method that you choose to segment the image with artifacts, will be worse than the same method using the images pre-processed by your approach, for example, right?
Yes.
The other things that I understood that you did not use this in the projection images. You use this for the already reconstructed image, right?
Yes.
The already reconstructed image. But what do you think about using this for the projection images? I mean, for the reconstruction itself.
Of course, it's a future. Yes, a future test, and this kind of work that you speak maybe can be a future project too.
Okay, yeah. If you have interaction with someone who work with reconstruction, right? Or
Yes.
even if you get the data for the reconstruction, so you can use this to compute the 3D reconstruction rather than post-process the reconstructed image. Because if you're able to remove the artifacts from the projection before you do the reconstruction, you'll no longer get these effects that you have, for example, when you have metal in the body region, right? Okay,
Yes.
that's interesting. The one last question here is I didn't understand actually. One of the baselines, the filtered back projection, is that the
I'm
baseline?
sorry. Can you repeat, please?
The FBP that
FEP.
in the table is the filtered back projection, the algorithm that is used for reconstruction.
Yes, exactly.
And how?
It's the representation of the observation data with noise. It's not
Okay. Okay, it's not the reconstruction. I see.
yes. It's a reconstruction method, but not I'm sorry.
Well, for the purpose of the work, it was not used for the reconstruction. It was used for
Yes.
doing noise. I see.
Yes.
Now I understand, because I saw that. I just say, oh, how did he measure the performance of the filtered back projection if he's working without projections, right?
Yes.
But now I understand what you say. Okay. So
if
thank you.
you
Okay, continue, Matthias. What are you
if
going?
we use the projection, the sinogram, we wouldn't put the FBP in the table.
I see. Okay, good. No, that's fine. So
Thank
thank
you.
you. With that, we conclude the talks of the day. And before we finish this session, I would like to thank you all for watching this session, and tell you that tomorrow at 9:15 to 10:30, we're going to have another session number 4 on graphics and visualization 2. So I hope to see you all there. Okay, bye bye.